and then do this. So welcome to this seminar at the University of Copenhagen with our viewpoint of Shuo Pang. We're trying to start this seminar again, this time with the recording switched on. And Shuo, without further ado, the floor is yours.
Yeah, welcome again to the second talk of my first for a clique problem, exact clique problem. And let's move on. Okay, so here is a plan of the talk. First of all, I will introduce what I mean by average case harness proof complexity. And then I'll tell you something about what the SoS proof system is, and then we dive into. Okay, average case harness. So our target problem is P, which is very famous. Given an n-vertex graph G, can you tell me whether there is a clique inside it? Where the parameter K is usually said to be, well, almost any value of K is interesting to us, and these are some common choices. And it's a natural question to wonder how hard is this problem on the random graph. So here is the most well-studied model of random graph, where you add an edge independently to the graph with probability P. Now you might expect that such a fundamental NDP problem to be hard on random graph too, but there is a so-called threshold result, which says as long as your P, fixed P, let's say a parameter, is not within the very thin range, then it's trivial to algorithmically tell the correct answer with high possibility. As long as P is above that threshold, you just say yes. Otherwise, it's a no. So it's amusing to think that if we let P to be above, to be below the threshold, then what is hard after all? If you say no all the time, then with high probability you pass. Well, if you think about it for a moment, then one way, probably the question is, well, to prove your answer in the most strict mathematical sense. This is of a similar flavor to the, let's say, the channel phenomenon in computational complexity, where the random function is hard by a simple counting argument, but given any specific function as a simple, given its truth table, then most of the time I don't know anyone can prove that it's actually computationally hard. Anyway, this kind of question points to the study of proof complexity. Now, a very short introduction to proof system from my point of view, or at least within the scope of this talk. So what do we mean by a proof system? Actually, any self-efficient proof checker algorithm gives you a proof system, where taking any string pair pi and tau, we understand tau as some claim and pi as a proof. If this pair passes P, then we say pi is a proof of tau. And it's for basic fundamental results of Copenhagen saying that if you have a proof system defined in this way, that always has a short proof for any tautology, true tautology tau, then P is equal to Q in P, and vice versa. In actual lower bound studies, we are considering much more concrete systems. And usually we will consider proofs that don't need quantifiers. They are called the non-uniform proof system, which is kind of analogous to the non-uniform computational model in circuits. And for slight technical convenience, we study refutations of the negational topology. But still, we will call them proofs and topologies without any kind of confusion. Then the main question we consider is, given a tautology tau and proof system P, are there short P proofs of tau? some examples of the topology in the system. So let's start with the topology. First set, namely, any unsatisfiable Boolean formula can be regarded as a negation of topology. This is kind of a universal family of instances, namely, you can encode all semantically interesting formulas to set in most of the time. And some more specific examples are specific families of topologies are listed there. For example, from counting, you can encode the pigeonhole principle. Namely, there is no one-one map from n+1 to n as a CNF or set instance, and try to refute it. Or typing, which is a mod2 counting, which says which says the negation of the double counting that if you add up the degree of all vertices in a graph, you must get an equal.
So the sound is really bad apparently. Did you check your audio settings, or could you do it very quickly now?
Sure. Let me leave it a response.
No, I think the audio settings is what you want to do. Just go to Zoom audio settings.
There might be problems with the sensitivity of the microphone. Either it's too high or too low.
Yeah. No, but it's set to automatically.
Is it because it's too?
No, I think what you can do is try to speak slightly louder, and then we can. I mean, we'll have to figure something out until next time. But maybe slightly louder. I don't know. Keep going, please.
Okay. So is my voice more audible now, or can I keep going?
Just keep going, please.
Sure. Well, so we see the families from counting, and then there are families, more interesting families from computational complexity itself. For example, the k-clique problem, which we will discuss in more detail in a minute. And also you can encode a circuit lower bound problem as a set instance. Namely, you just take a constant string of length 2 to the n that encodes the truth table of a function. And then you write down that there exists a small circuit computing this function out, and you try to refute it. This is just a formal way of what circuit complexity lower bound provers are doing. And the encodings will depend on our interests. Sometimes we encode it as stats instance, as we have mentioned. And sometimes we encode it in an algebraic way if the proof system we're considering is of algebraic nature. For example, here is an example of two encodings of the same simple raw topology. The first line says x1 is true and x1 implies x2 and x2 is false. This is the simplest example of induction. If you algebraically encode it, you can encode it, for example, at the second line, where 0 means true, satisfiable. And so the proof systems. The proof systems, there are a lot of them, and I won't go one by one. But the focus of today is obviously sum of squares, which is a definition we'll see in the next one or two slides. Just a reminder that here is the third one of Neustadt principle, gives an algebraic refutation of the above example. This is because if all the green axioms are satisfiable, at least you can set variables to 0 or 1 so that all the green equations becomes true. Then as a corollary, you shouldn't get a 1 equal to 0. But since this identity is on the other hand checkable by Neustadt, so this is a refutation, meaning that the right hand side cannot be 0 under any variables. And since we're talking about complexity, we also want to measure the proof. What do we mean by a proof to be short? And it's not surprising that there are many ways of doing that. depending on the proof system, of course, and our interest. And today we will, since we're talking about sum of squares, which is the algebraic system, our complexity measure of a proof will be its degree. Now here is a just an explicit expression of the average hardness problem of the. Namely, if we draw a random graph that is below the threshold, then we want to show that with high probability, although it's true that G doesn't contain a complete, but there is no short P proof, where our P will be squares. Again, I haven't actually tell you what is sum of square proof, but we'll see that first.
Can you try one final thing?
Yes, I see.
Go to audio set and switch off adjustment and set camera, microphone sensibility somewhere in the middle.
Sensibility. What is sensibility?
Yeah. And switch off automatically adjust.
What's interesting is that I cannot adjust the volume. Are things better now?
Increase it a little bit.
Are things better now?
Slightly better, but still increase a little bit.
How
Increase
about
it. No.
Keep going, please.
and this is the best we can do for now, I guess. Yep, so this is our average case hardness problem. And now the next is to introduce what is SoS. Also, there are some related algorithm problems that is related to the proof complexity of w-clique, but I guess I'll okay, sum of squares. The proof system actually comes from a family of algorithms, which is very powerful, especially for some important optimization problems that we're not going into detail. But in a nutshell, what these algorithms do is that given an optimization, that's a Boolean optimization problem, the algorithm runs a semi-definite programming on the variables that are low-degree monomials. And you have a degree parameter, namely the monomials that consider are of degree no more than d. More concretely, given the constraints that f1 equal to 0 and fm equal to 0 on variables x1 through xn, and an objective function f that you want to maximize. And the SoS relaxation or algorithm, it sets the variables to be all degree monomials. And then run the following semi-definite programming, where this green px represent any low degree polynomial. So it's really like telling me whether it's feasible if I set these constraints to 0 and set my objective value to c. And since it's an SDT, then morally this runs in time into the omega d. There is a lot of subtlety about this, and in some pathological cases, due to the magnitude of coefficients, is not necessarily true. But again, it's another of the concerns today. Okay, now SoS proof is a fairly straightforward translation of that algorithm, of what that algorithms do. Namely, given the same family of constraints, you can take into account, you can add one constraint expressing the objective value, and you want to find a one-line refutation that looks like that. where again everything is no more than d without cancellation. So this is the SoS proof system. And to express the clique problem in the SoS system, we have the following axioms. We first draw a random graph. Then according to that graph, I write down my axiom scheme. Here, the point is that the second family or class of axioms, namely the clique axioms, they depend on G. And of course, we set this, we want the family to be unsatisfiable. So our omega should be greater than what the threshold is set, namely greater than, let's say, 2.5 in. Then by counting, we know, or by probabilistic argument, we know with probability in this setting, the claim is, the axioms are not satisfied. But the question is, can degree D sum of squares prove that they are satisfied? Then we can, the system refuted in the previous sense. And here, for lower bound provers, the best thing you can get, or you can hope for, is to show that for omega that is even as large as 10 to the 1/2 minus epsilon, still to refute these axioms, you need a sum of square degree omega log n. And the reason is, first of all, let's notice that for larger omega, the easier it is to refute it, because you can always set some more variables to 0. And the reason why we can only hope for a lower bound of this form is that, on the one hand, if omega is, let's say, above n to the 1/2, then there is a degree D sum of square refutation with high probability. On the other hand, if D is above, let's say, 2.1 log n, then for any reasonable omega, there is a straightforward algorithm. Actually, it's a Nussbaum size refutation of these axioms. If time allows, perhaps we will. No, but not for now. So this is our target. We want to prove a lower bound that is close to the dream version. Let's see this. Equal to correct. So here are some previous lower bound results that we had. First of all, this is a almost tight lower bound, but it's for a weaker system called Loga-Schritter, which I won't define. And then we have results of SoS, which is a line of earlier lower bounds are proved for constant, mostly for constant degree D. For example, these two. For example, the first one makes both sense if D is constant, and the second one is proved for D explicitly for D equal to 4. Namely, degree 4 SoS is already interesting. And then was improved to the third one by slightly. The third one improved the first one by a factor of 2 on the experiment. And then came this celebrated paper in 2016, which proved the almost optimal lower bound for SoS system. The only catch is that they relaxed the clique problem formulation to be a form that is called non-exact, which we will see in a minute. And then we will show that for the original exact formulation of clique, qualitatively similar results, despite that we have a log-log-n loss. So what do I mean by a relaxation of the clique problem? Recall that in the clique formulation, in the problem from SoS formulation of this problem, we have a family that is a family of constraints that comes from the fact that we assume the clique size is omega. And now they do not allow this family, but we can assume an objective value alone. What does this mean? It means that the SoS representation cannot make any further deduction based on this. You cannot multiply and find out a polynomial and reason them together. No. And some reason that we care about this is the first one is if you view these representations from an algorithm point of view, then the exact version of this problem, or allowing SoS to do deductions with all axioms it is provided, it corresponds to a potentially stronger algorithm with almost same running time. And why not run them instead of reconversion? And also there are some downstream applications where the exactness or exactness matters. And perhaps most importantly, it's about technique. For many average case SoS lower bounds, the current techniques fall short of handling the exactness problem. And almost always, each problem itself requires a new idea. Namely, even if you already have a lower bound proof for the non-exact case, how to prove it to the exact case is completely unclear. And for clique, it seems to be known as a challenge. The reason is that the approaches to other problems before it, whose exactness issue is solved, don't seem to work. And actually with fairly good reason that they shouldn't. Here is what I think about previous problem. Here are some examples that are sought, whose exactness version of lower bounds are proved. As said, the methods for each are quite different. For random CSP, although I haven't introduced this definition, but let's describe it sort of vaguely. The strategy is it's actually a classical strategy where you break this objective function as a sum of local functions. By local function, I mean each function depends on a small set of variables. And this notion of locality is formed from graph expansion or graph closure, which is a familiar structure in that context. Another example, the second one, is called planted planes, and the argument there for solving the exactness issue is purely arbitrary. They use a projection operator, and the reason it works is because the norm estimates there are sufficient. Sorry, I couldn't go more into the details, but quickly move on clique. As for clique, we'll see the proof in a minute. And here is the mentioning of some more problems for which the exactness issue is not solved yet. For example, the independent step problem and sparse clique, etc. They remain open to the journey. Okay, now let's sketch a proof of a lower bound proof. First, let's sketch the strategy of a lower bound proof. First of all, what's good about SoS system is that there is a general receipt to prove lower bounds, namely duality. It comes in two steps. First, you construct a map that is called pseudo expectation from all the low degree monomials and extend it linearly, such that, of course, all the axioms should be satisfied. And the second step is that you want the resulting moment matrix defined in that way, where X subscript of subset of n means the monomial. You want to show this matrix is PSD under the definition. If you have these two, then it's not hard to see that there cannot be any SoS. This is nothing unexpected, namely 1 + 2 implies the result. If you notice that the condition 2 is just a matrix language of saying that all polynomial squares are assigned a non-negative value, using the fact that x sub a or x sub a times x sub b is x sub a union b, which comes from Booleanity assumption errors. So that is our goal. We want to find a magnitude and prove that matrix exists. Now, of course, the whole proof is about the actualization of this plan. Now, let's start with designing Tuda. First observation is that from the axiom that from the size axiom, we are forced to set the values of the monomials from a degree top-down way. Which means the problem is purely reduced to the problem about degree D monomials, degree exactly D monomials. And then we use the clique axioms, which tell us for any vertex subset S, the e to the s, remember, e to the s is a function of the sample G. It's not a constant. So we better view it as a function itself as a function in G. And now if you think about it as a function in G and a factor through the clique function, you better make it edge symmetric about the edges inside S. And if you write down that seriously in an algebra expression, you get a formula like that, where I will explain what F is. So basically, this formula says e to the SS should be in this form, where the coefficient before a Fourier character, which is the basis of representing a function on G, should be depending on only the vertex size. And there is a mysterious parameter tau that is not introduced, that was not introduced so far. And this is a closure parameter. It's slightly larger than the SoS D you're considering, but still no more than say log n over log n. And this is actually a similar. This kind of idea is actually appearing recurrently in the complexity world. And the idea behind it is that we make our pseudo-expectation design taking into account its value, taking into account all slightly larger subsets of the vertex set n. And only in that way we expect later the value we have or we get on the smaller subsets can behave in a better way. Namely, you need to expect or to get a result about PSDness from the values on subset of size D. You really need to start from something that is slightly greater than D. It's like a closure of those subsets and go down. And so what's left is to find a good function F so that the resulting moment matrix is positive. That sounds kind of easy, but if you expand the expression of the matrix, you get a formula like this, where the ij element has an expression as we have just in the way that we have just talked about, and explicitly look like that, where I do not ask to be the union of sets. And here is how the to be chosen function F here. We want this matrix M to be positive with high probability when evaluated on random G. So every entry of M is a set of function H. And what can be said? If you play with this expression around, you see that there is very little chance that you can find an F so that this expression simplifies to something. So we'd better go back to the high level, namely on possible methods of analysis, putting aside the choice of function F for a while. So previous methods divide roughly into two categories. The first one is what I call a vertex-based. The feature of that method is that they design an M which is different from us, and they hope that, roughly speaking, the expectation over G of that function of that matrix M will be dominating. It will dominate the pseudo-random quantity, the difference between M and its expectation. And then they transfer the analysis to the expectation of the matrix M. And the analysis there uses a special family of matrix called Johnson pieces, which themselves are PSD. So if you can express the main parts of the matrix, namely the expectation of that, to be a positive combination of these PSD matrices, then you're done. The drawback is that that kind of design, namely their method of designing M, inherently limits the quality of the lower bound. This is already demonstrated in the rear. And the second method is what I call edge-based or factorization method. It works by factorizing the moment matrix further into a LQL transpose form, so that for the middle Q, the oath regime could work. But the catch here is that this factorization is nothing simple. Namely, in this factorization, L and Q themselves have entries that are not constant but functions in G. And the way that these L and Q emerge, or these L and Q are defined from graph theoretic decomposition, which I will talk about on next. And the drawback of that method is that it's too rigid, in the sense that the graph theoretic decomposition can be built only if M, the Fourier coefficients in M, have a nice multiplicative form. And you couldn't hope to do any kind of perturbation or something of that sort to the moment matrix M so that the coefficients become nice. The reason is that the matrix M is pretty ill positioned, and this is special for the P problem. So that any kind of entry-wise approximation would almost surely fail. Here is the graph decomposition we use. First of all, by a ribbon, we say by a ribbon we mean a simple graph with two designated vertex sets, I and J. There is no condition between I and J. They could intersect, they could be general position. And I use the letter T to mean the edge set, to mean the edge set of the graph. And then we have the concept of minimum vertex separators. Namely, a vertex separator is a set of vertices in a graph such that the removal of them will block any path from I to J. And so we have the natural concept of minimum vertex separator. Namely, we count their weight and choose the ones with minimum. There might be many minimum vertex separator for a given graph G. But what's cool is that ultimately they form a lattice. I won't actually give the definition of a join and meet of two minimum separators in the graph, but I will only use the fact that due to this lattice structure, there is a well-defined notion of min element inside the set of all minimums and the max element. Let's look into a picture. Let's skip the words below, but look at this picture. The above figure, the figure on the first line is a ribbon, where the special vertex sets are I and J, and A and B, both of them are minimum separator. And actually, A is the leftmost minimum separator, which means any other minimum separator will be separated by A from I. And symmetrically, B is the rightmost minimum separator. And based on this graph decomposition, now using the leftmost and rightmost minimum separator, you can decompose that graph, that ribbon, let's call it R, into 3 sub-ribbons. Namely, the part between IA with special vertex sets I and A now, and the part between AB and the part between BJ. So that the vertex intersection of the 3 parts only happen in A and B, and there is no edge intersection. If there is an edge in A or in B, you put all of them into the middle part. This is a graph decomposition. The matrix factorization will be based on. Now, the idea is that the moment matrix M should be approximately, or can be approximately viewed as the sum of all the left possible ribbon for any global ribbon, times the sum of all possible middle ribbon, times the sum of all possible right ribbons. And if you express this idea in algebraic way, then roughly it says a Fourier entry at the Fourier term I, it should be T. Chi T at the ijth entry of M, it should be decomposed into a Fourier entry at the it should be a Fourier character at the I8 position of the left matrix L times the middle Fourier character at entry AB, then times the right Fourier character at entry J. And now you see clearly why they need the coefficient C in the original in your moment matrix M to be in a multiplicative form. It is exactly for the aim of making this decomposition. Fourier characters chi R naturally is a product of chi RL, chi RN, and chi R. But the coefficients, a priori, there is no condition of them. This is exactly the problem in this case. In our case, our CT, namely the Fourier coefficient of Fourier coefficient, it is in no way a product of local Fourier because they look like this. Here, I use the variable A to represent the size of the whole shape, size of R, and U is some constant minus the size of the union of I and J. They are both parameters that is concerned with the global property of your original ribbon. And in such an expression, it cannot such an expression involves the use of these parameters in a non-trivial way. And it's not too hard to see that there is no algebraic factorization of this expression into something that depends on the left only, something depends on the middle only, something depends on the right only. So we see the limitation of each of these methods. And now our approach on a high level consists of two parts. The first is that I still want to borrow some idea from the vertex part, but now I use the following way. I do it in the following way. I build a vertex part times edge part structure, or I find such a decomposition of the moment matrix M, where by multiplication I mean actually the matrix entry-wise product, which is actually an easier product to visualize. It's called the Adamar product. And the special property of this Adamar product is that it preserves PSD matrices. Namely, if A is a PSD matrix and B is, then their Adamar product is automatically a PSD matrix. But it turns out that you cannot do a one-shot Adamar decomposition of M. You somehow need a sigma pi for it. And later we'll see that this little MC matrix, this capital MC matrix has further property that is supported on those lines and columns that have intersection size of these. So they're a little bit more complicated. The little MC, as we'll see later, is somewhat easier to deal with. But for the capital MC, still their coefficients are not nice in any way, but they are nicer in the sense that now we can pass the analysis of their individual MC into what I call all of its localizations. And by localization, I mean, you look at, given the subset R of small size, you look at the from MC, I want to get a matrix called MC R, which is supported on all the columns and rows that contain this given set R. The reason for doing so is that I hope the coefficients, the coefficients of this MCR after localization will be more local, in the sense that I want to completely remove the dependence of the parameter U within the location. Now here is a formal expression of what we would do. The first lemma corresponds to review the sigma pi structure, and we handle each part of little MC and capital MC separately. Let's move on. For the first lemma, namely the little MC part, is actually easier, as I said. It is because the little MC will be defined to be the matrix of that. And by some algebraic manipulation, you will find out that it is again a positive combination of the Johnson pieces. So they are very positive from the algebraic nature of those Johnson pieces. This part has nothing unexpected. This gives us the first lemma. Now the capital MC, on the other hand, is this, which doesn't look quite friendly to us. But the stress is that although it still carries some information dependent on variable U, which is a global information, it does so in a lesser degree. And our next step, as mentioned in the strategy, is to fully resolve this dependence of U by a localization decomposition. So, given the previous combinatorial description of localization, namely we simply want MC to be the sum of MCR, we can actually calculate the coefficient, the entries of MCR using something called Euler transform, and the result looks like that. And as you can see, the dependence on U completely disappears. The issue that is left is brought by parameter A. Previously, we mentioned two parts or two variables that carry global information, and A is that is left. Now let's observe why this expression is better and could be put into work. Recall that we want to make an analogous LQL factorization of this MCR. In an ideal world, the coefficient of chi-t inside that bracket, in an ideal world, or just as in the non-exact case, the coefficient should be that something should be one. That something was one. And omega over a into A can nicely fit into the structure of a product of local information, namely omega over a into the left side, omega over a into the middle side, and omega over a into the right side. In other words, this parameter A, although it's global, it's a sum of local information. So if A appears purely in an exponent as an exponent, then you have the product structure. But now, back into the exact case, that something uses A in a completely different way. And as I said, at least as I see it, there is no direct approximation of expressing that something into either a sum or whatever of local products. But let us look closer. We can see that, again, as mentioned, all the issues are brought about by parameter A now. And our idea is that although A doesn't appear purely as an exponent, if we prefix the size, remember the meaning of A is the size of the whole ribbon. If we prefix the left and right sides of this ribbon, then the parameter A is something that could be told by solely looking into the middle part of the decomposition. Which means if we fix the left and right sides, then everything about A, you can put it into the coefficient of the middle matrix in the imagined matrix factorization of QL. Of course, there is a price to pay for this step. Namely, now, to realize this fixing something beforehand idea, the dimension of a matrix Q will be multiplied by the thing it fits. It becomes a blocked matrix. This is a reminder of what SCR is. But after skipping some heavy content to present here, the result is that we can still borrow the idea of matrix factorization with a twitch that the middle matrix dimension is slightly raised and it becomes more complicated. And of course, the reason we are doing all this step is that we hope this middle QCR to be still easier to analyze. Otherwise, it doesn't buy us anything. And this is the last step. The first thing that turns out about this middle matrix QCR is that the dominant case is actually C. That is the part. Sure. So we concentrate on this Q0. And the general idea here is, again, classic. We decompose this random matrix Q0R, or pseudo-random matrix, into a structural part and a pseudo-random part. For the pseudo-random parts, it's very sorry.
What is C? Subscript P.
In the first step, M is a sum of little MC times capital MC, where C ranges from 0 to half of D. It's an intermediate parameter. It doesn't have it. So there are two things as index C and R. No problem. The good thing here is that, okay, we're analyzing Q0R. As I said, C equal to 0 will be the dominant case. We use a structural pseudo-random decomposition of this matrix Q0R. And the good thing about the pseudo-random part is that they are well understood by norm control. It's because of the use of, we can use graphical matrices to bound the norm of the pseudo-random. And here I must remark that the notion of graph matrices, which stemmed from this paper, proved itself to be a very handy and even fundamental pieces for the analysis of these pseudo-random matrices. Because of we have very good norm concentration bound. However, the structural parts it might sound easier, but it is not, because it's quite honest. The thing appearing here is, I should say, it's a little bit unexpected. It turns out it had the quality of the structural parts. After we did so much analysis, it finally depends on our choice of the capital F function. If you remember that in the first step of your pseudo-expectation design. And this is what we will choose. And we will see. It turns out to be about very special structure, special matrix family, which I call factorial Hunter matrices. By analyzing now, we can get PSDs of the structural part, and hence the product might complete it. I'll skip the definition of graphical matrices, but we will certainly go into that because these become almost a universal tool for SoS, average case SoS. Well, I do want to show you something about the analysis of the structural part of Q. It turns out Q0R can be expressed in this form, where to appreciate its structure, let's look into a picture. Remember, our Q is a very large blocked matrices, and the black line means it's blocks. And for every subset, small subset A, there is a submatrix inside this larger matrix that is denoted as 1AA tensor something, and that something corresponds to the different figures on this in this picture. For example, for some A, it is represented by a cross, and 1A tensor something is supported on the position of these crosses. And for a different A circle, 1AA is supported on the 4 circles, and for a star, someone corresponds to the position of their star. And they together gives us a submatrix, which is the support of the Q. And our goal is to show that for every A, let's say a cross, the matrix that is supported on the position of crosses is PS. And later on, we sum up all for all A, we'll get a. Now, the matrix that appear on the, let's say, the position of a cross, crosses, it is what's inside that bracket, where matrix H has a very special expression namely its ijth entry, are some constant plus I plus j, then taken factorial. In general, a matrix whose ijth entry only depends on I plus j is called a Hankel matrix. So we naturally call these matrices factorial Hankel matrices. So the proof of the PSDNs boils down to prove that that bracket is. I will state very briefly in 2 minutes how this is done. If you observe those family H, for convenience, I denote HMC to be that matrix of dimension M. And our target PSD is the plus minus combination of these matrices. The first good thing about these special matrices is that each HMC themselves are PSD. This is a concrete demonstration of their PSDness when C is equal to 2 and 3 at dimension. But this is not enough, right? Because what we want is, as I said, plus minus combination of these matrices. And these matrices are well known to have very spaced spectrum. They are ill positioning, in other words. So if you do plus minus combination of a family of them, then perhaps for the end results in some unfortunate direction, you will get a very large negative eigenvalue. But quite fortunately, in our case, not only we can demonstrate the PSDness of individual such matrices, but also the demonstration we give satisfies certain recursive relations so that we can actually manage to show PSDness of their plus minus combination. And the recursive relation is this. In this example, it's demonstrated. The recursive relation is that for the side matrix of the decomposition of the second one, it's not only just some matrix, but it's the D above one, right, multiplied with a Jordan block. And in general, similar phenomena will actually hold. If you carefully write it down, use some related inequalities for some work, you can show the PSDness of this plus minus. So it is in fact true. And that concludes my proof. And very short summary or reflection. Conceptually, what we did is we combined two previous techniques, and then using product products and the notion of localization. Well, technically, things turn out to be very technically heavy. But among them, I want to raise two questions. First is that, is there any a priori explanation of the choice of capital? Or do any other choice? Does any other choice? And the related question is why factorial Hankel matrix appear in our analysis at all? Their appearance we counterbalance like an axis. But if you believe no axis can happen without an intrinsic reason, you should try to answer. And finally, open problem, except the really obvious one to remove the Lagrangian factor in degree. Another one that I'll bring up is the coloring problem. As said, there is for the non-exact version, the lower bound is known, and that was known due to a reduction to the clique problem. But that reduction seems to be for example.
Questions?
you can about exact coloring? Why can you not
because their reduction is quite.
No, not the reduction, but applying your technique directly to exact coloring. Have you tried this? Do you know what it is?
I didn't try a series. And I don't see, at least I don't see any easy indicator that it works.
Any other question? So then let's thank the speaker again. We're taking a 10-minute break before we resume the second technical half.